I'll introduce our next speaker. This is Geoff Unger. He's an IFMGA guide, Avalanche educator, and death metal enthusiast. And he is here to talk to us about the effects of latent snowpack on avalanche start zones. Welcome, Geoff.
Thank you, Steve. And thank you to ESAW for inviting me to this event. It's great to see so many familiar faces and also new faces in the room. So I've been accused of having too fancy of a title for my somewhat simple presentation. I think based on what we saw from Ned, we're going to take a step back in complexity in certain ways, but also look at very important aspect of our winter snowpack and talk about some of the considerations for what comes of our big winter from last winter in our start zones. Oh, didn't like me. Doesn't like the clicker. No, doesn't seem to. Oh, now it does. Okay. All right. So what kind of the seed for this presentation is from a friend of mine, Mike Phillips, who works on patrol at Mammoth Mountain. And he's like, hey, I really think about terrain differently when we have snow that remains from the previous winter on our runs at the mountain. And so I wanted to take that and also look at some of the considerations for us as backcountry users. And so this is my hypothesis that I started with. Like I'm pretty concerned about the steepening of the slope if we have snow remaining on the start zones. And so in this presentation, we're going to go through these 6 items or 7 items. First, we're going to get a background of some basics of terrain configuration. We're going to look at snowfall and snow coverage on the terrain. We're going to talk about how the snow gets redistributed. Then we'll look at the snow slope analysis of the snow that's remaining and look at some of the findings and other considerations. So one of the things that we want to look at here is our terrain configuration. And this is my representation of a flat slope. And this is what it might look like if we have homogeneous snowfall over that piece of terrain. Now, we also have these concavities in our terrain. It's another one of the basic setups. And this is what homogeneous snowfall might look like in a concave feature. Then we also have convex features and the resulting homogeneous snowfall over the terrain. However, we all know that in the Sierra and elsewhere, we have the effects of wind, and that redistributes the snow over our terrain. And that the snow may not fall consistently on our different features. That was a particularly windy day. So we have a lot of snow redistribution mid-slope, but also on the ridge crest. And so on the ridge crest, we have cornice development. And what that does is it grows the depth of the snow from the ridge itself to the point of the cornice. And so we have a thickening of the snowpack, and we have thinner snowpack on the leading edge of the ridge and also directly underneath the cornice. In our concave features, wind, even at a lower rate, will fill in these depressions. And so you can see that from our previous graphic, our snow is thickening in the middle of the concavity. And it may also take some snow from the point of the convexity and redistribute that downslope, or thin the snowpack at the stress point of the convexity. So this is a well-known piece of terrain around Mammoth. You can see Mammoth Rock in the upper left. And these are our cliff bands underneath and to the looker's right of Mammoth Rock. And so we're going to take some of these basic terrain configurations and then apply them with added snowfall in the terrain. And this is for reference here. Some of these cliffs are bigger than 30 feet tall. And so as the snow falls and lies on the terrain, it starts to surround the cliffs, and the promontories here are actually bare of snow. But as the snowfall piles up, this is from last winter, probably around the time of that day where there were a bunch of avalanches in the Sherwins. You can see that these 30-foot cliffs, it looks like ski terrain now. So if we are moving from our graphics from before with our different slope and terrain configurations, flat, concave, and convex, with cliffs being the exaggerated version of a convex slope, in a deep snowpack, these features get smoothed over and the snow surface becomes more homogeneous. So when we move from our basic models of snowpack and terrain configuration into what remains on the ground surface from last season, going into the next season, we're going to look through the slope analysis that I conducted of a couple of these terrain features, one from Mammoth Mountain, and two from the Sherwins. And these are the resources that I used to conduct the analysis. So if you are a frequenter of the ski area, you know this run very well. Dave's Run. And on the back side of this ridge, there's a massive fetch. Dave's Wave and the southwest face of Mammoth Mountain. And so when we're talking about redistribution of snow, this is ground zero for that effect. You can also see this is actually a pretty good photo illustrating, I think, my hypothesis that our slope angle is going to be steeper in the start zones of this terrain based on the shadow that's falling over some of this snowfield. So I attempted to look at Google Earth imagery and get a representative sample of what the remaining snow looked like live right now. But the most current image I could get was from August, and there was a lot more July, and there was a lot more snow up on the mountain, and the mountain was still more or less open at this point. Dave's Run, I believe, was closed, but you can see the strip of Cornice Bowl that they were still actively grooming. And the red sort of kidney bean shape is where I overlaid my representation of where I think the latent snow is. And so transferring that to CalTopo, the similar kidney bean shape, and then I overlaid a line where I think the main path of the run is. And from CalTopo, if we use a feature called terrain statistics, we can get a terrain profile for this line. And you'll see some differences between this line and the other lines that I took from the backcountry. I actually learned a little bit and shortened my lines to get a little more precise data from the map. But we also need to take into account that these maps are very coarse in scale. And so there's wide variation, or could be wide variation, in the analysis that we get from CalTopo. You'll also see on this photo, there are some red dots, and that's where I took terrain photos to show you later, standing actually in the terrain and taking some measurements. So here is the terrain statistics model from CalTopo. And I think it's important, like I said before, to take these a little bit with a grain of salt, because our mapping is not very precise, but it can give us a little bit of a range. And you can see the max and min slope angles and the average here. So standing in the terrain, I took some slope angles using my clinometer. And if you remember from ISSW this year, there was a presentation on the effectiveness of taking slope angle in the field, especially from a distance. And so instead of being precise with the angle, what I tried to do here is give these ranges of angle to represent what the change might look like. Ideally, you would go out and stand on the slope, but I'm recovering from a wrist injury and I'm not allowed to barely hike anywhere. So the next step could be to actually stand on the slope in the terrain with crampons and ice axe and measure the slope angle in different places on the snowfield. But as you can see here, I think that the ground cover is lower angle than what the remaining snow from last season would indicate here, in a difference of 3 to 5 degrees. And looking at this from a different perspective, obviously our terrain is not completely flat, but we have a steeper slope. If you put the clinometer against the grain of the underlying terrain, it yielded a mid 30 degree slope. But then as you put the clinometer on the surface of the snow, looking from afar, it yielded much more like a mid 40 degree slope. So I think we're seeing that if there was no snow there, our initial start zone angle would be lower in general than with the snow present. The other thing of note is that we have these concave features that when we have debris and latent snow, we have pooling of the snow, and that may create a different effect, and we'll see that a little bit later. So here are my two backcountry examples that I went to look at, and I chose these because they're close by, and later on in the presentation we'll get to how we might extrapolate this to other parts of the range. So again, we're looking at Mammoth Rock, and the right path is Upper Mammoth Rock Bowl, and the left is the main Abbey path. And from Steve's presentation earlier, we saw some notable events from the last season in these paths. So you can see at the top of the slide here, the town of Mammoth Lakes, or the edge of the town. And so these are features that are visible from town. So let's look at Upper Mammoth Rock Bowl first. There's a little bit different terrain configuration, and the snow is present in a different part of the slope than on Dave's. You can see that it's a little bit lower down below the ridge crest. And so here's my Google Earth image from July of this year, where there's still quite a bit of snow, and I tried to highlight where I think the remaining snow is now on this Google Earth image. I also used the same method in CalTopo. And like I said before, I tried to constrain my area of the snow and also my line on the map to get a more, a tighter sample from the mapping that's available. And what that showed was that we have a pretty big change in slope over that line from low 40s to upper 20s. And so what we're going to find here after we look at this is that when we take a slope angle in the terrain, we have a homogenization of the angle. So we're taking more of an average of the steepest and the shallowest. So that concavity is getting filled in. So the field truthing here was that the lower part of the slope here had an angle of mid 20s and the upper part had low 40s, and then the resulting snow cover made this a more homogeneous slope in terms of the slope angle. All right, so let's step over to main Abbey path. In the main Abbey path, both these panels are very small, but I think in the start zone as skiers, we're pretty vulnerable to the terrain features that we're in. So we do want to take note of these. So this is more of a broad, like if you're looking from town, it's a wider snow panel and a little bit shorter maybe overall. Again, the imagery is from July, and so we had deterioration of the amount of snow over time, but still remaining snow on the slope. So here is the CalTopo sort of kidney bean shape again of the remaining snow and the line of the start zone superimposed over the map. And so I think even through my progression here, I shortened the line even more, and I ended up with a much more closely knit block of slope angles by doing so. And it may also be that the terrain configuration is such that it's more consistent on the ground cover as well. So you can see that instead of having a range of 10 or 15 degrees from the minimum angle to the maximum angle, we have only 3 degrees here. And what I want to point out here is that standing at the top, at that saddle above the main Abbey path, there's a flat bench in this snowfield that's about 50 or 60 feet below the ridge crest. And so if we link that back to what Ned was talking about in terms of the snowpack always moving down the mountain with glide, that's probably where we have our cornice that was built up at the ridge level, kind of moving down slope here. And so that creates that bench feature. And it was visible in the Dave's example as well. So here's our terrain analysis on this one, mimicked our measuring of the slope angle mimicked what we saw on the CalTopo for the ground cover. But then we also see that flat bench had a like pronounced sort of cornice-like feature, and the slope angle was actually steeper with the snow remaining in the terrain. All right, so let's look at these graphically, or at least in a simpler form. So on Dave's run, we found that, or I found that the slope angle was greater in certain aspects of the feature when it was built up over time through redistribution of wind from the previous season, and the remaining snow made the slope angle in the start zone steeper. In main Abbey path as well, the shelf feature is pretty interesting and more pronounced maybe in this one than you could see in the previous photo, but also a steepening of the start zone in this path as well. And then in our Upper Mammoth Rock Bowl, we had more of a concave feature and snow remaining on the slope that made the slope angle more consistent over the terrain that we measured. And this would kind of link with our theoretical snow coverage model from our concave features in general. So overall, I think my limited sample size, through that limited sample size, I did find that there was a steepening of the slope angle in these start zones, but obviously we would want to pay attention to our terrain configuration and how the snow was laying over the terrain in each specific case as we start to extrapolate into other terrain configurations and other places in the range. So I think there are a couple of other important considerations with our latent snow from previous seasons that I want to go over that are also important to look at alongside the slope angle consideration. The first one is the ground cover. And so if we have rough and rocky ground cover, then that can anchor our early season snow. But if we were to have remaining snow, that creates a smoother sliding surface for our potential avalanches. And so we definitely can see that in this Upper Mammoth Rock Bowl example, where we have rocky terrain on either side of the remaining snow, but then quite smooth feature or snow surface when we have the snow left over. The other thing about this, maybe I'll go back one, you can see there's little patches of snow here on the side of our snow field. And so going into the winter season, we get these early season snowfalls. And I've done some analysis of terrain and how the snow lays over the terrain in a different talk, where we get early season snow and certain aspects and features hold the snow more than others do. And it's my hypothesis here that these snow fields hold the early season snow a bit better depending on their location in the terrain, partly because they're elevated, but also because they are more reflective than the surrounding rock is of radiation. And so we see snow that's in the sheltered areas, but we also, you can see the new snow is covering the old snow here in a thin layer. And that leads us to consider how that might be changing over time when that new snow sits on the surface of the old snow. And a common process here is faceting. Near surface or the old snow may act like a crust because it's quite firm and doesn't accept as much transfer of moisture or radiation as a lighter wintertime snowpack might. So at that interface now, we're looking at development of facets. And so when we get our initial snowfalls of the season, then we're looking at not only a smooth sliding surface, but a potential for persistent slab avalanching. So the next consideration here is that of spatial variability. And so this is Mount Wood and Parker up north. And you can see in the north-facing terrain, we have features that are both down low in the terrain and sheltered that are holding the snow. And these are aligned more with our concave features. And then we also have features up near the ridge, which are behind a giant fetch again, that would be more consistent with our Dave's Run or our main Abbey Path features, where we would have buildup of snow and steepening of slope angle in the start zone, potentially. The other thing we want to take into consideration is orographics. So basically, if we're on Mount Wood or the Mammoth Crest, or this Sherwin Ridge, we might be closer to the trailing side of the range. But if we were to step forward to the Mammoth Crest or even further, we might have more accumulation of snow. So if we think about that, we probably have more remaining snow in these places that are deeper in the range. Whereas if we drive up and down 395, we're seeing more the amount of snowfall like this. And so if the further back into the range we get behind this eastern Sierra slope, we would have more incidents of snow remaining in that terrain and more features that would hold the snow that we're talking about. We also want to think about the variability up and down our range here. And some of that might have to do with the orographics, but we do have different snow depths and distributions in the northern part to the southern part of our forecast area. So if our common storm track is coming from the southwest up the San Joaquin River drainage, Mammoth is right on the crest, and these other areas have less of a direct storm track from the southwest and may have different snow configurations and snowpack depths. So I looked at a couple of other features from afar. This is Bloody Mountain, for those of you who aren't familiar, but we have similar patterning of this deposition of snow with both ridge crest remaining snow and snow in the tight concavity of the main chute of Bloody Couloir, for example. The other thing I want to talk about, well, here's the Mammoth Crest. So this is an example of how we saw a couple of more patchy photos from Mount Wood and from Bloody, but as we step to the Mammoth Crest, even a short distance away, you can see that every single feature has snow in it, and the volume of snow is greater, I think you would find. So I also want to point out the outliers. And so this is the Kidney Chute up north of town, north of June. And Mount Dana is in the background. And the Dana Plateau, again, is a huge fetch. And so we have also this feature in the Kidney Chute that there's kind of steep cliffy walls on our looker's left side of the terrain feature. And so it makes it seem more like a northerly facing aspect in this terrain feature, even though the actual run itself is more of a southeast or east feature. So it's a little more of an outlier compared to what we are looking at in Bloody Couloir, which is like very deep and dark and north facing, but we can have these remaining snow fields in places we might not expect. So what I want you to take away from this presentation is that we do have some impacts from the remaining snow from last season in our start zones and in our terrain. And most of those are things we really need to pay attention to as we get out into the snow and start skiing and recreating in the backcountry early in the season, especially, but maybe thinking ahead to later in the season as well. And so what we want to do is use our terrain photos and look around when we're driving and not just maybe pull over and get out the binoculars, right? And look at some of these features that are holding snow from the last season. Take some pictures and try and map in your mind where these features are. And then if we have an idea of where the snow is remaining from the previous season, we can use some of our online tools like CalTopo or other visualization methods to help get an idea of recognizing the patterns of where the remaining snow is in the terrain. And as we start to get out there, maybe check my work, see if I did a good job of explaining how the snow is going to lay on the terrain and how the slope angle steepens or doesn't in these different features. Thank you.